Hello everyone, welcome to this lecture on material selection. Now that we all have a working familiarity with various classes of materials, including their strengths and weaknesses, and furthermore their typical properties, it's now time to review the ways to specify them in a design. This lecture elaborates further on the laboratory exercise that was carried out earlier in the course, providing an in-depth description of how material selection specifically applies to the design process. The French mathematician Jacques Hadamard made many pivotal contributions directly to the field of mathematics and indirectly to the ways in which many engineering problems could be solved. He defined a well-posed problem as one that which both has a solution and is unique, and that the solution is completely dependent on the inputs to the problem, constraints or other aspects which define the problem itself. Considering the choice of a material to be applied for a given application as a problem statement, it is fairly clear that it's not a well-posed problem. There is most certainly a solution, but that solution is most certainly not unique. Take, for example, the material choice for a bicycle frame. Engineering or manufactured materials such as steel, aluminium, carbon fiber reinforced polymer, titanium, and even natural ones such as bamboo have all been proven viable for this application. Regarding the aspect of whether the solution is dependent on input or problem definitions, that aspect still holds true for material selection, other than new variants of materials and material systems that are constantly being devised. As will be shown in this lecture, the key to a successful material selection process is getting the problem definition closer to being well-posed rather than being ill-posed. The problem of choosing a specific material for a specific application is ill-posed. That is, it fails to meet the criteria for a well-posed problem as described previously. There are an immense number of materials which are available to be selected from. Furthermore, for any given class of material, or material family, metals, polymers, and ceramics, there is a direct relationship between their structure and processing history, which can in turn decide the properties and how they perform. When factoring in material systems such as composites, then the number of choices expands dramatically. Each class of material and combinations thereof have their own benefits and detractions, beyond things such as properties and performance. Some materials are significantly more costly than others, both in terms of currency, but also potential environmental costs. There could be some aspect of the design that requires a specific manufacturing technique which is not applicable. Therefore, one requires a framework to guide a design or component through a selection process that weighs the relative pros and cons to ensure that the right choice is made. We need to constrain the problem correctly to limit the number of choices that need to be considered in a design process. There are many descriptions of how a design process should operate. This is just one. However, the starting points remain the same. There is some product which meets a need. This need is converted into a problem statement, and then there is some process by which a solution to this problem is developed, realized as a product. There is an iterative approach by which a concept or concepts are realized and then refined in a detailing step. Where material choices typically fit within this iterative process is that a material family is decided at the conceptual phase, metal, plastic, ceramic, or combinations thereof. During realization, an alloy class, polymer, or ceramic is specified. For example, steel versus aluminium, or a thermoplastic versus a thermoset polymer. Finally, a single material is specified, and this could be a specific alloy, a 6000 series aluminium, or ABS plastic. The rationale behind these choices requires deliberating on singular merits of materials, and there's nothing particularly incorrect about this approach. However, it may discount other viable choices in its approach or impede the design process. There is a companion methodology that can run in parallel to this process, which addresses some of the shortcomings of comparing the merits of singular materials. Starting with all materials occupying a search space, a translation step is first taken to provide a framework to screen all material in the search space which does not meet design objectives, and finally permitting ranking. With this process, many materials can be compared at once by systematically applying constraints to the selection process. Let's start first with reviewing the translation process. The translation process consists of 4 steps. First, the function of the component is described. Next, there are constraints to account for, and for completeness, including anything which is a hard limit, desirable, versus nice to have and negotiable. Next, the objective or objectives are defined, what needs to be optimized. Finally, free variables. These are factors that can change. This could be related to geometry, not a direct material consideration, or a tolerance for stiffness versus strength. There could also be other regulatory aspects, costs or manufacturing efficiency. Further to this translation step, screening, ranking, and finally validation takes place. These steps will be covered specifically in the second part of this lecture. The translation step is the one that sets up the basis for screening and ranking and further validation, so that's where we'll start first for a simple component. An automotive tie rod is a component which connects the steering box to the steering knuckles, such that movement of the steering wheel communicates with the front wheels of a car. It operates under both tension and compression depending on which way the wheel is being turned. A simplified cross-section is provided, which includes 2 diameters. Regardless of where one looks along the overall component, there will be a stress which develops as a result of force F in tension, as shown, or in compression, acting across diameter A over some length L. We can now describe the function, some constraints, an objective, and what the free variables are. We can say that the length is fixed, the cross-sectional area can vary, but it can't fail under load. Furthermore, it would be nice to minimize mass, as it's a transportation application. Note that there are no constraints on the material choice. One could state that it needed to be metallic or ceramic or some other aspect. Note that cost is not included as an objective, but that could be included here as minimize mass and cost. We have what we need now to formulate a performance index. The first step is to generate some equations which reflect the constraints and objectives, with some guidance from the free variables. If we don't want the tie rod to fail due to plasticity, then any force being applied over any area must be less than the yield strength. That handles our constraint. Next, if our objective is to minimize mass, then we'll need an expression which identifies what it is. The volume is the area times the length, multiplied by the density. We need now to combine our objective expression with the constraint. Modifying the expression for the constraint gets us an expression for the area in terms of force and yield stress. We can eliminate the area from consideration as it's a free variable. The other free variable is the material choice. Therefore, the material choice will be bound by a selection of material on the basis of yield stress and density. Separating our constrained objective expressions such that geometry and loading are separated from material properties, it can be seen that if we want to keep a constant mass, then as the density increases, then the yield strength can decrease. And if we want the density to decrease, then we need to increase the yield strength. The objective, however, is to minimize mass. We now have a performance index. If we want the mass to decrease, then we need to find a material with a high yield strength with a low density. Let's see how we can now use this index coupled with the constraint. The failure strength is something that can be applied to all materials, even if they do not exhibit a yield strength like metals and polymers. If we plot this strength versus density, we can compare a wide range of materials all at once. The relationship between density and strength is made apparent by our performance index, and we could further screen on the basis of our constraint. That is, the material cannot fail for a given load. Our performance index stipulates a 1-to-1 relationship between density and strength, so anything above the 2 lines as depicted will be suitable. This methodology works even if there is a non-linear relationship between a pair of material properties, and we'll get into that in the second part of this lecture. So, to review, the material selection process is an integral part of the design process. Without constraining our choices, or a selection process absent of a structured approach, will lend itself to being very ill-posed. In this part of the lecture, we've described how an overall selection process operates. This process starts first with translating the design problem into an expression or expressions which allow for constraint and objective statements. And these are balanced against the functional requirements and the free variables. We've also seen how this exercise generates a materials performance index, and had a cursory glance at how this index is employed to select a material. This is an aspect that we will cover in much greater detail in the second half. Until next time.